So I'd like to introduce Dr. Jacob Martin to the stage. He's going to be talking on the updated chemical history of a candle. He's working at Curtin University in the carbon group in the physics department, and is also associated with the hydrogen storage research group. And I'm sure he's going to give a good introduction to himself as well. So welcome to the stage.
Great. All right, so hopefully everyone's been enjoying this nice fireplace and on a nice warm day as well, which is very good. And just to add on to that acknowledgement of country, knowing that the traditional owners of this land hold fire in a very sacred place. So just a reminder of that as we go through this. So, as mentioned, I'm going to be talking about candle flames. And just a little bit about myself before I go straight into the history. So I grew up in New Zealand, you may hear the accent, and then went over to the UK for my PhD, where I did a lot of work on combustion, as you will see. And we're going to go through way more combustion than you thought was possible. So this here is a candle flame inside the lab. We've got lasers shooting plasmas into it. It was awesome. It was a great time. And I've come here to work more on the material science, which we will get to at the end of this. But this talk really came about because during the pandemic, there wasn't too much to do. And a few teachers that were talking to me really wanted some material that they could allow their students to do at home, and then we could talk about. So the experiments I show you are kind of an extension of those, and hopefully, if I explain them right, you might be able to do them at home as well. Also, throughout this talk, we will be using some ancient technology, so just bear with me here. If you want to pass out these here, you have to make sure you put the right colour on the right side. Here we go. Yeah, so let me just get this right. Yeah, so it's the red on the left.
Red on the left.
Yeah, so just make sure you fold it with the red on the left. And confirm for me that you can see that, wait. Yeah, I'll do that right, yeah. That's popping out of the screen for you. All right, now don't do that for too long, because you might have a bad time. All right, so there's only a few times, only about 4 times throughout this that you'll need these, but I'm just keeping them handy. All right. So let's get started. So Michael Faraday in the 1840s started to lecture on the chemical history of a candle. And he actually did that a few times, and it was in 1860 that he kind of did that. It was actually his last lecture that he gave, and it was put into a book in 1861. And you can see this here. I don't know how many of you have a copy of this or read this, but it's a beautiful book explaining the principles of the scientific method through the example of a candle. And this is the way that he begins the lecture, so I thought it's only fitting to start there. There is not a law under which any part of this universe is governed which does not come into play and is touched upon in these phenomena. There is no better, there is no more open door by which you can enter the study of natural philosophy, which he means science, than by considering the physical phenomena of a candle. And hopefully I'll show you that holds true today, just as it did in 1861. So we're going to start off by recreating some of Faraday's experiments. As you can see, I have nothing here to recreate them, so it will all be done on my slides and with videos. And I also want to show you some new wonders that have emerged inside the candle flame. So hopefully you'll enjoy this as much as I do. So let's start off with Faraday's first experiment. This is actually a very old experiment, first described by Aristotle. You blow out a candle, you get the wax vapor, the white wax vapor trail that comes up from the candle, and you get another flame, and you can reignite the candle by igniting the wax vapor. If you haven't done this, recommend it. It's very fun, and you can actually make it jump quite far if you get a really big candle with like a really good wick on it. So I recommend that. The other thing that Faraday did is he put a clay pipe into the base of a candle and was able to extract some of that white vapor and was able to split the candle in two, thus demonstrating that it's the the wax vapor inside the candle that is allowing it to burn. So I wanted to kind of think about doing some of these experiments at home, and this is the experiment I came up with for school kids. This was actually in Singapore when I was in Singapore. So tea light candle, which is an old form of heating actually for tea. And you can see the tea light just normal, taking the wick from out of the candle there, having the wick by itself, and this one's quite fun. This is foil covered with the wick just poking out. All right, and I asked the students which one will go out first, in which order, and I made them make predictions, and a few of them were correct. You can see here there are, I think we had about 7 classes that were all on Zoom, and they all individually did those experiments, and then we collated the numbers. So let me show you what we got. There we go. Classy lighter there. Oh, okay, that one doesn't light. I should have made you guys vote on this, but I didn't want to embarrass anyone, I thought. I think you do quite well. All right, so we're going. I'll just. Whoopsies. 1 second. Trying to be too clever here. All right, there we go. The first one to go out is the foil-covered one, and then the wick by itself. And then our trusty tea light is still going. All right. So here's the results from the different classrooms. We got a bit of variability, but I think in general, this one was seen to be the one that goes out first, followed by that, and then this one never even lit. All right. You may have predicted that. But let's go through why that happens. So you actually need to heat candle wax and vaporize it before it will combust. Here is some wax, paraffin wax on a heated, I didn't do this experiment, on a heated, just a hot plate, and you've got some vapors, and when you ignite it, you're able to burn that. But you see the flame goes out, and the reason for that, there's not enough heat in the flame to sustain the vaporization of the fuel to produce the vapor needed to burn it. And that's why we need the wick to enable that. All right. Yep. You can see that the wax is coming off of the wick because that's where it's being generated. So let's go into that in a little bit more detail with my terrible handwriting. Forgive me. So the candle is hot, as you all experienced as a child, putting your finger in it. Very fun. It's producing a lot of heat, and that heat radiates down and melts the wax. So you get a pool of wax at the bottom here, melted wax. And then that melted wax gets sucked up the wick via capillary action, and inside of the flame it's heated and the wax evaporates and you get the wax going into the candle. Great. So when we block when we block off with foil, we actually block all the heat from the flame, melting the wax at the bottom here, and so we no longer have any melted wax, so we have no fuel for our fire, and it goes out. So that's quite fun. And I did this with the kids, but I wanted to go further, and I was thinking, can you block the thermal radiation from reaching the wick, right? All right, so this is my construction here. So this is actually a little hood made out of foil that goes on top of the wick, and I've pricked small holes inside of the foil there. So the fuel can get out, but most of the thermal radiation should be blocked. And we're pretty happy. We're burning. So why does that burn? Well, the wick is actually heated via convection, via the hot gases hitting into the foil, which then vaporizes it, while the wax at the bottom here is heated via radiation. So it's heated by the infrared light from the candle. So that's a nice little subtle difference of how things are heated there. Right, and we all know that hot air rises, so that's not too surprising. This here is a Schlieren video showing the change in the refractive index of those of the hot air that's rising above the candle. And this is actually why it's got that tulip shape, because air is being drawn in and being pulled up, and that is actually forming that tulip shape that we see with a candle. And if you take a candle into space, you find that it doesn't have the tulip shape, it actually is a sphere, which I think is quite wonderful. So this is actually on the Challenger space mission. They lit a candle for someone's birthday, I believe, and it was a sphere. So this is an experiment hopefully most of you have had a go with, smothering a candle with a jar. Super exciting, this one. And it goes out. Okay, so we all know it reacts with oxygen. But let's see if we can see that happening at a smaller scale. So inside of the wax we have got a whole bunch of paraffin molecules, roughly around 20 carbon atoms long. This is one of the paraffin molecules. They're all kind of packed in the wax. They melt, moving past each other, get vaporized, and then this guy here is going to go in and burn in the flame. So we're going to, I've taken a smaller molecule here because it's a little bit long to do the whole C20. If you want to put your glasses on. And there's no way to turn that off. We see 3D. All right. So what I have here is pentane with a whole bunch of oxygen around, and we're going to have a look at it burning. This is with a in the computer. This is actually just done on my laptop. It's not particularly complicated calculation. Something called molecular dynamics. You can see them moving around. We're getting 3D. Oh, okay, we're speeding up now because, you know, it takes a while to burn this. So I've just sped it up. You probably won't be able to see too much at the moment, but you'll be able to eventually see hydrogens coming off. There we go. I think I saw a lone hydrogen running around, and you'll notice here that the fuel has broken down into two fragments. So this is one fragment, and then this is another. So this is fuel pyrolysis. Once the hydrogen comes off, you get something called beta fission, where the fuel dissociates into small fragments. And this is why all fuels burn the same way, because all the fuels will dissociate into the same maybe 10 different compounds, around about 2 to 3 carbon atoms in length. And if we keep going, you might see some water running around there. Here we go. This is the end of the simulation. You see some CO2, we've got water, and we've got some carbon monoxide. If you kept going, you would get all of the carbon monoxide turned into CO2, but that is a slow reaction. So if we go back here, you'll notice condensation on the outside of this jar, so that's the water as well. So you can take those off, and hopefully no one is feeling ill. We're all good? All right. Okay. So let's do another experiment. So this one here is slightly modified from Faraday's. Faraday actually held a piece of paper inside of the candle flame, but again, I thought that was a little bit dangerous for kids to do. So we have here a mesh from a tea strainer. All right? And we're going to take the lighter and we're going to place it inside of it. Now you hear that noise? That is the extractor fan going, because I don't want to breathe this stuff in. All right, so what are we seeing there? We're seeing that where the flame touches the mesh, it goes out, and that's because the heat gets sucked out of the flame. And that means that we can look inside of the candle, and we can see that the candle is actually hollow. So the fuel's in the center, the fuel is in the center, and then it diffuses out, and then the oxygen that's coming from the outside reacts with it. And so the flame is in fact hollow. And this is actually, this effect of the mesh was used by Humphrey Davy, who taught Michael Faraday, who was in the Royal Institute before Faraday, to build a lamp that was going to be safe in a coal mine. So imagine this, you've got open flames. How are you going to stop that open flame from igniting a huge stream of coal gas that comes through your mine? And the way you do it is with a mesh. So if you just have methane and a candle, it's not looking good for your life, but if you blow that methane inside of this Davy safety lamp, you can notice that the flame is contained within that mesh. And this saved hundreds and hundreds of people around the world. So it's a very, very important discovery. So what else is inside the flame? Well, when I did this experiment, you will have seen black smoke coming out if you looked carefully. This is soot, and it's not good for you. That's why I had the extractor fan on. And if you put some metal inside of the flame, you'll also collect soot. This is actually how they used to collect ink. I will talk about ink at a point. You can put your hand very quickly in the flame. Don't hold it there, please. And you can collect some of that soot as well. To prove that the flame is actually there are actually particles inside the flame, you can actually use your phone just to shine on a candle and you'll be able to see the shadow. And that means that light's being absorbed by particles inside of there. And that was actually done by Hooke in 1600s. And so black soot is present in the flame and it's heated by the reactions that I just showed you. Until it's yellow hot. So it's kind of like a piece of metal in a hot coal fire. It'll heat up and it will go red, and then it will go yellow, and then it'll go white. In the case of the soot, it's heated up to yellow hot. So there was a lot of interest in preparing a non-sooty flame, which is a non-luminous flame. So this would be a luminous flame, and then this would be a non-luminous flame. And Bunsen developed with his technician developed it, and he claimed the glory, but he developed this Bunsen burner. And there's actually some subtlety to this that I don't know if it gets taught all the time. If the tube is screwed into the cylinder, which is this thing here, and the city gas, which is a mixture of methane and carbon monoxide and hydrogen, is allowed to flow into it, it sucks in so much air into the opening that it burns at the mouth of the tube with a non-luminous, perfectly sooting flame. The trick here is you use a jet of methane, and that jet entrains air. It creates a vacuum, pulling air into the hole here, and that provides the air required to enable complete combustion. And by changing the air openings in the bottom, you're admitting different amounts of air, and you can make the non-luminous flame. And of course, that was used for flame emission spectroscopy, which I'm teaching in this in the course in chemistry at the moment, which is great. This is a great instrument here. You can see the candle. That's actually a reference candle, so that it allows you to compare it, and you've got the Bunsen burner here. So it says non-luminous flame, but it's very much luminous. So you can see green and blue emissions. So what's going on here? It's called the swan bands, and it's due to, the green colour is due to C2, excited C2, and you've also got CH, which gives you the blue emissions, and the OH also gives you that blue emission. So this is a chemiluminescence reaction here. Right, another thing that you might not have seen before is you can actually separate the Bunsen flame into two parts. So if you have a tube down here and you have another tube of a different diameter, you can stabilize the OH flame up here, and you can stabilize the CH flame or C2 flame down here. And if you increase or decrease the amount of air, the soot begins to form right here. So it's clear that it's in the place where the least oxygen exists. That's where you start to see soot form. Of course, the candle has got that emission, that CH emission. This is a filter showing that CH emission, and a terribly trimmed candle. So if your candle looks like this, please cut. Oh gosh. All right, we'll get back to that. That drives me nuts. Okay, so what is the structure of a candle? As I mentioned, the blue-green area here, the luminous zone, oxidation. This is the temperature profile. It's actually hottest kind of around the edges here, and when you get up to here, it's getting quite hot. It's not the blue zone. Gosh, how many people I've seen teach this as the blue colour is the hottest. It's not. It's chemiluminescence. So what was motivating Faraday is he was a bit confused, because carbon monoxide and hydrogen, which you can produce from coal by heating it up, that burns with a blue flame. But if you get this coal gas, pipe it up, into a lamp, it's quite luminous. So what is causing the luminosity in this? And if you can make it more luminous, that would actually be beneficial because they needed more lighting. So he actually distilled out of that coal gas what he called bicarbonate of hydrogen, which is benzene. And this is actually his original vial of benzene that he purified. And he showed that at the beginning of the 1800s. And the first thing he mentioned about benzene is it makes a lot of soot. So this here is just a petri dish full of benzene, and whoever did this wants to die because the kind of carcinogen content of burning benzene. Anyway, hopefully they had a really good extraction system. So burning benzene, and then if you burn hexane, you'll notice that immediately you've got soot forming. You don't have this dark zone. So that makes you think maybe benzene's important for how this forms. Something else that, 3D glasses. Get ready. We've got some calcium carbonate. Calcium carbide, thank you. Right, so we've got carbon and calcium, and this was actually made in one of the first batteries where you basically put two carbon arcs together, put a bit of lime in there with carbon, and you'll produce this, this compound. And if you drip water onto that, you produce acetylene gas, and that acetylene gas can be turned into a very nice little lamp. You can take your glasses off now so you don't feel sick. You all with me? No one's feeling giddy? Good, okay. So, and actually this is very similar to a reaction that we're studying at the moment for sodium borohydride, where we can drip water onto it and make hydrogen, which is great. And that would be a lot better than burning and creating a whole bunch of CO2. So it's actually a similar reaction. And this little burner is quite fun because you can change with the dial here the amount of water that drips in, and that changes the amount of acetylene that's pushed out of here. And this is a miner's lamp. So acetylene, benzene seem to be important. What impact does pressure have? This is a fun experiment. These two decide to climb to the top of Mount Blanc in Switzerland and burn a candle, because that's what you do, right, when you're a 19th century scientist. All right, so they get up there. No one was doing this, by the way. This is a modern picture. So in burning candles upon the summit of Mount Blanc, I was much struck by the comparatively small amount of light which they emitted. Now, why that's surprising is that it burnt at the same rate. So it consumed the same amount of wax during the time up on the top here, but the big difference was that as you lower the pressure, you get no soot. Now this would suggest that there's some sort of condensation mechanism going on. The fact that there's such a strong pressure dependence means that it's like some droplets are forming. So Franklin actually predicted that there were droplets forming in the flame, and it was actually only later that they proved that actually in here they're solid. So they're solid particles. The way they proved that was a wonderful experiment using polarized light. I can go into it, it's fun. Higher pressures, you get more soot production. So this is really what was known at the turn of the 20th century. Acetylene, benzene seem to be critical. There's some threshold that we don't understand, and the pressure seems to impact it. So let's just step sideways or tangentially to thinking about these pigments as inks. So for a very long time, lamp blacks were collected, where you just get some metal and put it in the candle and collect it. And then you can create an ink that you can write with. And this was big business in the Middle Ages. Pine resin. It's really only in the 1920s onwards that you start to get a lot of these made. Most of the mass of your tyre is actually carbon black, which is surprising. And so a lot of the research in the early 1900s was on this carbon black. This is a big furnace that creates it. This is a modern process. You've got a natural gas burner, and then you put gas in here, oil, sorry. You spray oil in, and then you create your carbon blacks. So I managed to find this great old picture here. This is the first ever electron microscope that was built in Germany by Ruska. And they were at a high voltage lab, and they were able to create electrons in a vacuum tube, accelerate them towards the sample, and then image them on a fluorescent screen here. And this is a picture from the 1938 magazine Electronics that shows that in operation. And the first picture they took with it was of soot. Isn't that great? So they put a wire mesh in there, and when they zoomed in, they found that soot was made up of these tiny little particles. These particles are only about 20 nanometers across, so super small. So here's some different carbon blacks in the electron microscope. This is actually a scanning electron micrograph of carbon black. You can see it's made up of these spheres. And the difference between carbon black and soot is that the soot comes with a whole bunch of crap. So you can see here, that's the technical term for it, brown carbon or tar. And this here is actually where all the carcinogens are. So you've got benzene and all sorts of fun stuff in there. So people started to think, well, what's happening with the atoms inside of carbon black? So using X-rays, they suggested, well, there appears to be, from the X-ray pattern, that there are small bits of graphite that are kind of misaligned. And people thought about how they could be cross-linked, but they didn't really understand what they looked like. So to find out what they look like, they used even better electron microscopes. This is from the 1960s. This is one of the early Siemens transmission electron microscopes. And in the first ever phase contrast image, they also looked at soot as a test object. So, you know, seems to pop up again. And what they found is that these little platelets are arranged in a kind of concentric fashion. This is an instrument I used during my PhD. It's the Techni F20, beautiful instrument. And here's some pictures we took of different soot particles as you go through the flame. And at the low parts of the flame, we found that they were actually quite curved, the little bits of graphene, the little bits of carbon. This is something more modern. This is the new electron microscope that just got installed at UWA. It's beautiful, beautiful instrument. And you can see here the sample. This is actually a sample that I'm looking at. I think that's soot. I'm pretty sure. So you can actually see. I think that's quite cool, right? It's like you're eating dinner but there's soot on it. Great. So one question I answered during my PhD was, how, if you were to grab it in your fingers and squish it, what would it feel like? Would it be soft? Because if you kind of feel soot, it's quite soft. And so there's some great experiments where they actually got a little indenter and they squished the soot, a single soot particle, which is really cool. And they measured the force on this probe. And we did the same in the computer. We squished it. Graphs indicate that if you were to squish it in your finger, it would feel like charcoal. It would feel really hard. It's actually a hard material. There's lots of cross-links. We can also burn soot in the TEM. This is some work from some colleagues of mine, where they burnt soot inside of, I think this is a TEM, and you can see that as it's burning, it kind of goes away, I suppose. It's a very technical description there. So that's kind of fun. You can also do it at high resolution, and this must have been very, very hard measurement to do. You can see it burning away there. So we're getting pretty good at seeing what happens. So let's just talk about what the smallest soot particles are quickly. So that was found out in the 1970s using these beautiful argon air lasers. And basically, you can see from the scattering how big the particles are, and they're on the order of a nanometer. The other cool thing you can see is that they actually fluoresce. So the nanoparticles fluoresce green, which is due to stacked aromatics. And only in 2007, they were actually able to make a whole bunch of fluorescent dots out of candle flame, candle soot. And this has actually opened up a whole new area of making carbon nanodots for biomedical applications. So again, some new insights. So yeah, they're quite small. This is atomic force microscopy. And some helium ion microscopy, you can see these tiny little particles. Again, some molecules here. These are sort of the molecules that you see in the flame. And these molecules get a bit bigger through, this one here in particular can give you cancer through this mechanism. If you want to ask me about that, I can tell you more details. How do the molecules get bigger? They grow by eating acetylene. Right. This is quite fun because there's a 3D picture. All right, so you're looking at C60, the soccer ball of carbon, and this was discovered in 1985, but in 1987 it was discovered that all candle flames have got this molecule inside of them. So, we're all good? Yeah, cool. So this is the molecule, it's this beautiful ball, and now all fullerenes, which are quite important molecules for solar cells, are all synthesized in a benzene fire. Imagine doing the health and safety for that. And here's some modeling that was done by another group where you can see how they grow and curve, and we did our own kinetic Monte Carlo modeling of showing how this works. So this is a modeling approach. And in the 2000s, we got to actually see the soot molecules starting to cluster together. So you can see here that the mass of the molecule that comes together to form soot is about 500 daltons. Looks a bit like this. And this is really where we got to in about the 2009, 2010, when I sort of started thinking about this. We didn't really know how soot formed, which was pretty embarrassing. Because as you can see, we've done a lot. And there were two main approaches to how we thought they'd come together. Either you form droplets, which is that idea of the pressure dependency, and that won't work because they're not sticky enough. So these things boil at a couple hundred degrees, soot's forming at 1,000. So that's not going to work. These reactions were all found to be too slow, chain polymerization. So this was quite embarrassing in the combustion community because we didn't know how soot forms. We knew a lot about, and now you know a lot, maybe too much, about soot. But anyway, I'll keep you going. We really care about it because it impacts the climate. So it's the third biggest contributor to global warming after CO2 and methane. It kills us. So the biggest correlation between death rate and pollution is the amount of soot. And it makes us more susceptible to respiratory viruses, which is a bit awkward with COVID. But the good thing is that if we can stop soot from forming, we can take PM 2.5, which is 2.5 micron or smaller soot particles, this is 2019, and reduce the pollution quite quickly. So this is during the pandemic, right? So it actually goes away quite quickly. CO2 is still there. Don't worry, we won't get rid of that this easily. It's much harder. So I just want to tell you about one last little fun thing here, which was actually seeing the molecules in the flame for the first time. So this was done, a collaboration that I did with IBM. So this is IBM in Zurich. And they were able to make a AFM that was accurate enough to measure the molecules, aromatic molecules. And this is what we found. So these here are actual images, pictures of the molecules in the flame. And which is great. This made me very happy. So you can see here, this is a schematic from a review article. It's 55 pages of glory if you really want to dig into it. And the molecule that I got most interested in is this guy here. So this one here looks kind of ordinary, but it is far from ordinary. It's quite remarkable. And this molecule, I think, holds the key to what's going on at that stage, which we still haven't quite figured out. So this is what it looks like, and it's quite a funky molecule. It's got sort of extra hydrogens here, extra hydrogens here, extra hydrogens here. No, there's only got one hydrogen here. It's quite funky. And using the computer, we can compute where the electrons go. And we discovered that the electrons don't pair up. They actually separate, and you get two reactive sites on the same molecule. So this molecule is like a barrel of monkeys, because each molecule has two reactive sites which can link up with other molecules that are the same. And we could do simulations where we could see how they react. So this is actually a full quantum mechanical calculation where these two molecules are interacting and reacting, using the full description of how the electrons interact. So if you're looking here, you can see the bond form there. And what was so exciting is you see how they kind of do a little dance first? Condensation, pressure dependency, right? And then they form a really strong bond so they don't dissociate. So this combines the physical and the chemical mechanism together in one. And this was actually originally proposed in 1977 in a review article by this guy who is a Kiwi, like myself. And yeah, anyway, it's got like 20 citations from, so like no one read it. And anyway, I got to meet him in person recently and tell him that we found his molecules, so he was very happy about that. We can get rid of these by just adding ozone to the flame, and a patent that I recently found, they don't know why this happens, but I think we do know now, they could get an 80% reduction in soot emissions from a diesel under high load condition by adding ozone. So that's quite promising. I'm working with some colleagues to see if we can rig that up. So the last bit of 3D is I want to take you inside of the wick of the candle. This guy here, which we also worked on. Oh, don't get your glasses on. Get your glasses on. Okay, we're ready. Okay, the piece de resistance. I have to go a bit faster because I did this very poorly. Here we go. Oh. Actually, I'll just play it. I'll see if it's going to go slowly, but maybe that's good for people not getting ill. So you can see that these sheets are curved and they're all connected to one another. And we're kind of zooming through like we're Ant-Man, if anyone's watched the superhero movie recently. There's no quantum realm down here, don't worry. We're now going into a slit-like pore. This is actually where molecules get trapped inside of charcoal and porous carbons that you use under your dish sink, for example, to filter your water. And we're also exploring how hydrogen can be stored within these pores at the moment, which is important for storing large amounts of hydrogen. It's a bit slow, sorry, I really should speed it up, but anyway, no one sick? Yeah, I might go just a little bit faster on that, because we are, there we go. Through we go. This is actually a screw defect here. A screw defect. We also discovered these also in graphite. Through the screw defect there, and we finish up in this nice little cavern here. My student said it looks a bit like molecular caving, you know? And he actually put some bat noises into the app, which I was quite proud of. And just to, this is the picture rendered beautifully. So next time you look at you can take your glasses off and not feel so sick. You can all, yeah. This is a picture here of inside of that coloured by the curvature. And so next time you look at your candle that's been blown out, you can say it's still beautiful, just underneath. I did mention I would mention this horrible, crap here. You need to chop that off, okay? Trim your wicks. Very important. But what you've got here is actually carbon turning into a solid here. It turns out this is the process that we're currently using, we're wanting to use to convert natural gas directly into hydrogen. So if you could turn natural gas into hydrogen and a solid carbon, then you can stop producing CO2. So this is something that Veen is working on at the moment, and in the Hydrogen Storage Research Group is what we're attempting. But again, in the candle, you can see it work. So this is where we're at. We've got big supercomputers. This is the one at Curtin's campus. Enormous instruments. This is actually on the International Space Station. This is a stadium-sized instrument. There are 4 of these around the world that have dedicated flame lines. And this is where I'm ending. These are the 2 different things here. And I thought I'd just finish off with a quote from Michael Faraday, seeing as that seems an appropriate way to end. I express a wish that you may in your generation be fit to compare to a candle, that you may like it shine as lights to those about you, that in all your actions you may justify the beauty of the taper by making your deeds honourable and effectual in the discharge of your duty. So enjoy that, and here's the last picture. Fire in 3D. I bet you've never seen that before. Anyway, thank you very much.
Thank you so much for that brilliant talk. We've got plenty of time for some questions from the audience.
One perhaps very naive question.
Yes?
You talk a lot about the senses and how you can see the flame by 2 different instruments.
Yes.
Is there any way that the sound of the acoustics is important for the way that you understand flame?
So the question, just to repeat it, is there any importance of the acoustics on how the flame works and the soot as well? Yeah, so there are actually experiments happening on the International Space Station at the moment where they do actually put acoustic waves into the burner, the bottom of the burner, and they see how the flame flutters. And by looking at the fluttering, they can understand different kind of more difficult things to see than if the flame is just in a constant configuration, or if it's all turbulent. It's very hard to do anything when that happens. But there are burners you can buy that have speakers locked into the bottom of them, and they sort of bob up and down, and it's very entertaining at conferences to see what they run through it. Rock metal is apparently. The flame really goes for it. It's very entertaining.
I've got one for you.
Yep.
So you're saying about there's 4 instruments around the world, 4 synchrotrons. Which ones are they that have this capability?
Yeah. So there's one at Argonne. There is one in California. There's one in this one. The one I showed you is in France, and then there's another in China that have, and I mean it's incredible, they can pluck molecules from inside the flame and then use synchrotron light to ionize them, and then they can measure exactly what the molecule is using, I mean it's wild, yeah. It's super cool. But I'm having a bit of trouble with the synchrotron people at the moment because the way they do the extraction, they don't see the large molecules, so they're convinced that the large molecules don't exist. And I was like, but we took pictures of them. I mean, they're there, right? But they're like, no, they're not there because we don't see them in our mass spectrometer. And I was like, well, you need to upgrade your mass spectrometer because they're definitely there. Anyway. Mm-hmm.
I guess, given the future of it's the early days, will you actually be able to make enough hydrogen to actually run, I guess, mobile equipment and so on?
So there are now many companies. Praveen just sent me a company today that's just started up doing methane pyrolysis. At the moment, those companies, there's only one company that's actually supplying hydrogen at a large scale, a ton scale, and they're making carbon black for tyres, and it's called Monolith Materials. And we're actually I had a chat to their engineer recently about it. They send their hydrogen to a coal-fired power station. And actually they're decommissioning the coal part and they're going to run it on hydrogen. So and they're using a plasma technology which is quite energy intensive, but they do produce a very nice product which seems to help them. So I would say at the moment we're seeing it at large scale, but you do see sort of, I think on one of the space missions they had a system where they were producing hydrogen by converting methane directly into carbon in a small unit, but we haven't seen that yet. But that would be great, just replace your natural gas burner at home with, that thing.
I'll ask another question now. So, I loved your videos and your 3D images, and with a lot of these molecular dynamics calculations, it's very intensive, having to use supercomputers. How did you render these 3D images?
Yes, no, it's a good question. So a lot of there's many programs that you can download. So maybe I should go back one step. We use supercomputers to basically describe the interactions between the atoms, and we let those structures that you saw self-assemble. So we don't put we try not to manipulate it. We just add the atoms randomly inside the simulation and let that structure evolve. And then we compare it with experiments to make sure that it's as close as possible to reality, which I did show a little bit of that. And then what we do is, so we can see we're getting some of the ribbon textures here, and that's what we see experimentally. We get the foamy textures at the low densities, and that's also what we see. So we do that, and then basically I put it into a software called VMD, which is basically, it's like a computer game software. I mean, some of the first ever graphics done on computers were done on molecules because they're super easy, right? Balls and sticks, and I mean, it's pretty simple to render. And then you just click a button that says anaglyph, which is the 3D glasses effect, and you can turn it into 3D. So it's really very simple.
That's really cool. Let's see how many other people start to use this in their first.
Well, I mean, it's old technology. I was like 1950s. Yeah. So I mean, this is not new. But I do use this in lecturing to show students things in 3D. I also have VR headset and some other types of things, but I thought it'd be a bit hard with a large group. So we go back to the old tried and true.
Right. Has anyone else got any other questions? If not, I'd also thank Jacob again for his excellent talk, and hopefully we'll have some pizza soon. But thank you very much. Gift for you.
Yeah. Thank you very much.
There you go.